Hey there, chicken fanciers. Let's continue our progress through the file. We'll be talking about Booleans next. Before we go through, there's a break in the file where we talk a bit about homework submission. I'm not going to go over it in super detail. Basically, there's a bunch of markup in here and comments that you shouldn't mess with. A lot of it'll be fine. The grader we're using for the first section of the course doesn't actually care about it at all, but later on it will care about it. General rule, don't delete stuff you don't know about. I think it's just a great policy. Occasionally we'll ask you to define an exercise, and it's okay if you can't do it, but you'll need to supply something of sort of the right type for us to give you sort of any credit at all. So there'll be instructions about that later on. Some exercises will be marked as optional. You genuinely don't have to do them. They will not be graded. You can always add new definitions, but every time we run the autograder, it's going to be on only your current file. We're not going to save your old files to sort of compare against, which is a blessing and a curse, right? So it's a blessing in that if you get something wrong, you don't keep paying for it on every homework going forward. But it's a curse in that, well, if you defined a helper function that you really like and you want to keep it, you're going to have to copy it over every time. The good news is the autograder will tell you when something's messed up. So just pay attention when you're submitting your files for grading, and you'll quickly see whether or not everything's okay. Shouldn't be too big of a deal. If you have questions, don't hesitate to ask on Zulip. Okay, let's move on. I wanted to find something that I think you all have already seen, but I'm going to go over a little slowly just to make sure we all know what we're talking about. These are the Booleans, named after George Boole, English pastor who invented the idea of truth and falsehood. That's not true. He was the person who sort of came up with algebraic rules for reasoning about ideas of truth and falsehood, but I think people have known about that idea for quite a long time. Okay, how do we define the Booleans? In languages you've probably already seen, they already exist, right? Like in Java, there's just Booleans, true and false, type Boolean. In C, they reuse integers, right? And so it's 0 is false and every other number is true. In Python, you have capital T true and capital F false. And so there's a variety of things that show up here. In JavaScript, they're lowercase. Here's how we do it in Coq. Now you'll notice we're defining the Booleans ourselves. That might come across to you as a little bit funny. And you know what? It is a little bit funny. Coq as it stands comes with almost nothing. We define everything ourselves. And that's strange, right? You would think a programming language would come with batteries, but it also speaks to the power of Galena as a programming language and Coq as a programming environment, that we get to make up our whole world ourselves. And that is in line with Coq's goal of being sort of a mathematical support system where the way mathematicians work is making up a world, a sandbox, and then playing in that sandbox. Okay, so here's the inductive type for bools again. You can compare it with day up above, where we have the inductive keyword saying, hey, here's the vernacular command, I'm introducing something. Here's the name of my type, I want to call it bool, because who has the time? I mean, if we typed these extra 3 characters, think how much more typing we would do all semester. It's utterly outlandish. So we'll just do bool. George Boole's last name had an E on the end, but that was the 19th century. These are different times. Bool is a type, and it's got 2 members, true and false. Great. We can work with these just the same. Here's a function that returns a bool. Is weekday. It tells us whether or not a day is a weekday. So for Monday through Friday, it returns true. Saturday and Sunday, it returns false. Look at that for a moment. Right, we can recall, okay, this is definition, that's a vernacular command. Is weekday is the name of the function. D is its parameter of type day, and it returns a Boolean. Here's the definition. We're going to do a match on the day we were given, where for each case we say, well, if it was Monday, we'll return true. If it was Tuesday, we'll return true. If it was Wednesday, we'll return true, and so on. If it was Saturday, we'll return false. If it was Sunday, we'll return false. There are shorter ways to write this function, and we'll learn them as time goes on. Okay, let's double check that Coq is happy with it. Is weekday is defined, right? If we scroll up, we'll see that's all it told us. We would have gotten like the bool recti and bool rec and bool end earlier when we defined bool. We can define a bunch of other Boolean operations. So here's negation, right? Not. So the language that you have used before this probably used a bang or something like that, or maybe the word not, something like that. So here it is. We're going to call it neg b, negate Boolean. It takes b, a Boolean, and then it returns a Boolean. And at first, we'll just use a match, right? Look at b. There are 2 ways to have constructed it. Either it's true, in which case we'll return false, or it's false, and we'll return true. Now, we also have if-then-else syntax. So if b, false, else true. Now, one thing worth noting is Coq if I sort of just go there, Coq doesn't have what are called one-armed ifs. Else expected after. Yeah. Every Coq program always has to terminate with a value of an appropriate type. So if you left off the else, what would we return, right, if B were false, right? There's no else branch, we wouldn't know what to do. Other languages will let you do that. You simply wouldn't do anything, but there's no not doing anything in Coq. This is sort of another characteristic of functional programming languages. It's probably different from what you're used to. As we go forward, we'll get more and more used to it, and we'll see sort of the implications of what this design decision means. Okay. But anyway, if then else, right? You might have seen this before, something like if condition, do some stuff, else if other condition, right? You have some syntax like this, right? Maybe other stuff, else, right? This is sort of like a C-like syntax. You see it in JavaScript and other languages like that. That's fine. Yeah, we just write it a little differently. It's just syntax. Okay. So another way of expressing it is through what are called truth tables. Right, so this is our little ASCII, little UTF rendering of a truth table, where a column is representing a variable. Here's a column representing B. And then we'll have other columns for sort of the operations we care about. So this truth table is a sort of a graphical representation of what Boolean negation is. So how does it work? Well, what you'll do is for each variable in your truth table, you'll write up Booleans T and F, right, to represent true and false, just shortening it just for space on the screen. And then for every operation you care about, you'll write another column for it. So it's saying, hey, when B is T, neg B will be F. That is, when B is false, neg B will be F. When B is false, when B is F, neg B will be T. Okay, that is a truth table. And writing these is a really convenient way of quickly expressing things to other people. And these are basically something you need to memorize, right? So you need to know the truth table for negation, right? This is a thing every computer scientist can simply produce. So as you progress in computer science, we're going to expect the same thing of you. Okay, here's another definition, and B. Right? This is a function that takes two arguments. It takes B1 as a Boolean and B2 as a Boolean, and it returns a Boolean. And the idea is this should compute the and. It should return true when both of them are true. Otherwise, it will return false. So let's walk through the code right here. Match B1. Look at B1. If B1 is true, then return B2. If B1 is false, just return false. Okay, you might wonder, why didn't we write something like this? And well, think about it for a second. Well, look, if B2 is a Boolean, if it's true, then we'll return true. If it's false, then we'll return false. Let's just return the thing itself. Why bother with any of this if-then-else shenanigans? Okay, our definitions go on using match here because that's what we wrote, but you should feel free, of course, to use if-then-else. Okay, so when you're building a truth table for something that has more than one input, your truth table has to have every possible input configuration accounted for. You need to cover all of your bases. So here's the ordering that I like to do. So here you'll look at the column. So B1, there's the column for our first input. B2, there's the column for our second input. And now here's the result we get, and B, B1, B2. You'll notice I'm using the space for function application rather than the mathematical parentheses that you might be used to, and B, B1, B2, or maybe the more programmatic B1 and B2 that you might be more used to. We'll talk about that latter one in a bit. We're not going to do the first one at all. So I really like this ordering. True then false, left one goes first. So I'll do all of the B1 true cases before I get to any of the B1 false cases. And then for each case of B1 being true, I have to look at each case of B2, right? B2 could be true when B1 is true, or B2 could be false when B1 is true. All right. The way that I think about truth tables is I basically memorize just the output column for the basic tables because I do the left-hand sides the same way every time. I recommend you do it this way. If you do it a different way, that's fine, but you really want to be methodical. So in the comments, we remark on how electrical engineers tend to go the other way because false is 0 and true is 1 in a circuit. So you want to count up, and that's fine if that's what you're used to. Maybe you've seen it before. Maybe that's just what you like. That's all fine. I think what I've done here is the most conventional. What's important is being systematic and doing the same thing every time, not any particular ordering. That said, the ordering I've used here is, I think, the most common ordering in computer science. So what I was saying, though, is I'll memorize this last column. So, for example, true, false, false, false. False, false, false. Did I say false enough times? Let's pretend that I did. That's the truth table for and. It's only true in the first row when both B1 and B2 are true. Okay, here's or. It's not pronounced orb, though that would be cool. It's just or B, or Boolean. Takes two Booleans again, returns a Boolean. If the first one is true, oh, we're good. We don't even need to look at the second one, right? Because this is an inclusive or. Either one can be true. If it's false, then we need to rely on the second one, again, doing the just return it trick. And here's its truth table. It's kind of the dual of and, right? Where and was false most of the time and true only in one case, or is true most of the time and false only in one case when both of your inputs are false. Okay, both of these are nice demonstrations of multi-argument functions. We can see how to apply multiple functions. We've already seen it in the notation here, but let's see it concretely. Let's compute a little bit. If I compute or be true, true, it says down here on the lower right, the answer is true. Okay, what about true, false? It's going to be true or false. Think to yourself for a second. Pause the video. It's true. Also true. What about this last one? They're both false. What's it going to be? Look at the truth table. Look at the function. Okay. So it turns out Coq is super extensible. We can create this notation x and y or x or y. And now we can run things like this. Right, and so now we have that notation. So you have the more conventional notation that you might be more used to over here. Okay, you might have noticed that we write in the comments things in brackets when they're meant to be code. So just pay attention to that. Okay, next up, this is the first exercise. So every exercise will be marked off like this, right? It'll say exercise colon with a bunch of stars before it, and it'll say some number of stars, and then it'll say typically standard. It might say optional. It could say recommended or advanced also. You can ignore those last two. If it doesn't say optional, this is an assignment for credit. And here it gives the assignment a name. Typically, if you're defining a function or something, it'll be the same as that. Okay, then we'll have some text that says, okay, here's what you need to do. So here, we're asking you to define and, which is the negated and. It should return true. Here's the description. The function should return true if either or both of its inputs are false. Okay, now there's some like funny stuff here. So these bits are the scaffolding we talked about of like, oh, don't mess with these. Leave all that alone. That's for our grader. This bit is where you need to fill it in. So what you need to do, it says replace this line with colon equals your definition, blah, 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 and then it says admitted. You want to delete this whole line. So Control K deletes a line. And then I'll say colon equals, and now I need to say something. And it's like, okay, well, what are we going to do? I'm just going to say true. That'll be right some of the time. We want it to be true if either of the inputs are false. But we can just do this for now. Okay, so we can see that Coq accepts it. Now, that's not going to be right if we look at the computes. If either or both of its inputs are false, we should return true. We shouldn't be returning true now. So my constant true function here is not quite right. So you'll have to fix it to get these to pass, to give the right truth table. But you'll do something like that. Now, it may happen, I'm undoing, oops, with Control /. It may happen that you get stuck on a problem. In that case, leave it like this, and then you'll get as many points as we can possibly give you for it. If you start to do a definition and it's not working, comment out your partial definition and change it back to this period with no colon equals and admitted. Otherwise, the code won't compile. Okay, that's the first exercise we saw. Here's another bit of notes on truth tables, building more interesting ones. There'll be a not-for-credit exercise sheet of just working with truth tables. So if you wanted to build a truth table for a more complicated expression, the key is you want to have a column for every possible input. So here, if we have an input B and we want to compute the truth table of or B, B neg B, you'll want a column for this other sub-expression neg B, and then you can use that to conveniently compute or B. Okay. There's one more exercise here, having you define implication. And it has the same truth table as this. So we're asking you to not just define it as that. We want you to give it a real definition. Try using a match or an if. But to get the truth table for implication, you'll have to write this down. I want to give one word of advice here. The truth table for implication is very counterintuitive, and people really struggle with what implication is. We'll talk about it a bunch more as the semester goes on, but it's a thing that really is just worth memorizing. Okay, so much for talking about Booleans, functions, and truth tables. I'll have just 1 or 2 more videos coming for day 1, and then that'll be that. All right, see you soon.